Let me actually see where okay. Um, I listed the reference so DeepSeek, we all know come from China, and they have very good performance and surpass GPT OpenAI O1. And so that got a lot of interest. What we are going to look at is the R1 itself, but also it's where it come from. Like the foundation model behind the R1, that is DeepSeek V3 version 3. And before that, there's a DeepSeek V1 and V2. So I'm going to give a evolution about this model and see how and why it achieve a good performance. Then we can also discuss what will happen next. So that is, I think, people are most interested in. Now, I want to first give a little bit of background for why it's interested. So I will start from the beginning of 2024, early last year. By early last year, in the middle of 2023, Llama 2 was invented. That is the best open source model by that time. And until the beginning of 2024, Llama 2 is the standard for open source. And then in the closed source, we have GPT-4. At that time, is the best performing model. And so the consensus is the open source model is much more inferior to the closed source model. And as you can see, they can do a little, they are about 20%, sometimes 30% behind the closed source model. And particularly, even for closed source model, the mathematics and the coding are not satisfactory. So that's the state of art at that time. Now, the beginning of 2024, I think the whole year of 2024 is the development of open source model, and what we see the ultimate success. What we see this last week, January 22, which is when R1 was DeepSeek R1 was released. That really demonstrated that open source model has come a long way since the beginning of the year. Now, in order to first let me explain. In order to compare the all the models on the same like in the same framework, we use evaluation data set. Particularly for the DeepSeek R1, they use the MMLU, which is a college level exam, which include chemistry, physics, biology, economics, different subjects. They also include the mathematics, including the grade school and the later high school mathematics. There's also common sense reasoning. There's also coding. So that is the base for all the model compared to each other. Now, during 2024, there are quite a few attempts in continue to evolve the open source model. So Llama 2 from Google was, but they are very small. It's 9 billion, 27 billion. Llama 3 came out in April 2024. And still, they are much better than their previous version, but still not as good as what we observe, like 90% accuracy. So yeah, so actually let me give you, I think this will give you a historical view, very much clear in terms of the timeline. First, let's focus on the Llama model. So from Meta, we know Llama 2 was released in 2023. And then we have, then the DeepSeek version 1 for today's model, the first version was released in January 2024. So their first version was actually a very small 67 billion model that essentially trying to mimic Llama 2. So they have identical architecture, identical activation function. Everything is the same and even smaller, a little smaller. So 67 billion. That's the first version of DeepSeek V1. And then we see the Llama 3 developed after Llama 2, and I will show you some additional advancement in Llama 3 against Llama 2. So with Llama 3, the training token started to increase. So with, let me see, with Llama 2, there are 2 trillion training tokens. But by Llama 3, with Llama, Meta started to use 15 trillion training tokens, so way larger. And that shows the significant improvement on the model performance. And the main is when you train on a lot of data, the model become better. So DeepSeek V2 developed after as a second attempt to try to improve on top of DeepSeek V1. So by the time we have in June 2024, the second version of DeepSeek was a much larger model. It's 230. Let me see. It's I think I have the number somewhere. I will show you. It's more than, it's about 200 billion parameters. So it's a very large model. Because it's much larger, they introduced this concept called the mixture of expert, where you do not always use all the neurons. You divide the neurons into experts, into subgroups. Each group is expert. So I will show a little more on. Just we will come back to this timeline later. What we see is the open source model on Llama side continue to develop. So in July, Llama 3.1 was released. They released a very large model, 405 billion. That one is actually approaching the GPT-4o performance. The later and December, end of 2024, the Llama 3.3 was released, but they only released a smaller model. Maybe it's because for the open source community, people they think people only run if they want to run on their own machine to be cost effective. 70 billion is sufficient. So that is what's behind the Llama development. So on the other hand, the DeepSeek going from 200 a little over 200 billion, now it's 671 billion in version 3. So that is a way larger model. Normally, you cannot fit into one laptop or one H100 GPUs, and you need a way larger, way more GPUs to fit this, right? Unless you compress it or get a distilled smaller version for that. The full version is 671, much larger model. And R1 is an improvement. Essentially, it's more fine-tuning, more adding more training data to this V3. So they are the same model. The R1 and the V3 are identical models. So that's the timeline. And so maybe I'll make this more visual. I will show you yeah. So this give you actual size for the model size going from V1 to R1. The started with the 167 billion to the 236 billion, and then now it's 671 billion. I think it's the largest open source model out there. Typically, when you look at the Grok, which open sourced ones, Grok 1 was open sourced. All of them is around 400, no more than 400 billion. So I think when you try to push the performance. There is a law, scaling law, that the larger you are, the better performance it will be. So we are trying to really push the performance to have way more parameters. The downside is certainly is, can you actually run on your own laptop is cost effective? I think that's the question we want to ask. So let me actually go back to introduce the um introduce what we see, the particularly the performance improvement, and all the development of V3 DeepSeek V3 to R1 actually followed a very similar development as Llama 3 to 3.1 to 3.3. What happens is, in the beginning, first of all, it's one language, then becomes multilingual. So in DeepSeek-R1, we have English, Chinese. It's actually only two language, but they are able to do long context, up to, they can process up to 128,000 tokens in the input. So that's the major development. The in the open source model, which is very impressive. In terms of performance, the smaller model, like the 3.3, 70 billion, trying to push the performance in MMLU, which they're getting there, but it's still not there. So it's 86, and the coding math still a little bit behind. So what we really want to compare for DeepSeek-R1 is to a very good closed source model called O1. So O1 came out in OpenAI came out O1 in September last year, and this is the first model that shows that we reach the almost a human level performance. For example, in the PhD, in the GPQA, which is a PhD level science data set, they outperform the expert human in the PhD exams. In the math, they read the competitive math competition, they reached 83, 83, and then before that, the GPT-4o is only 13, so it's a dramatic improvement. So this is really a landmark for every open source model trying to match. And also, we mentioned the coding in the beginning of this year was very poor, but now we reached 89 percentile in the all the participants. So this is just a breakdown in terms of the data set, where what's inside the data set in terms of different subjects, from both college exam and the PhD exam. And so I want to show you actually, I have the picture here. Yeah. So what is really impressive for DeepSeek now, before I go talk about the actual mechanism, is if we just compare the performance of between DeepSeek R1 and O1, you can see this model, this closed source model actually matched O1, almost identical. In a few cases, a little bit better than O1, but in a few cases, worse than O1. But on average, I think it's matched. It's almost identical. So that is very encouraging for us to see. This is why the excitement is. We know that O1 is a very powerful reasoning model, and it's closed source. Nobody has access, right? We only subscribe, so we don't know how large is O1, how it runs, even though there is a little bit of explanation on the reasoning process, but OpenAI never released the actual architecture to the public. So the real question is, can the open source community actually catch up with this? So I think what really for the people get excited is now we actually see the possibility with the open source model we can match what's behind the curtain. However, there's a catch here is I know when we say open source, there are three kind of open source. One is you open source just the model, like a DeepSeek. You can download the model, but you cannot see the source code. So the first the smallest open source is just the model itself. And the second level of open source is you can also see the source code. I think like GPT-2, and then I think Llama, we were able to see the code. Gemma is also, we were able to see the code. So I think that helps the community much more if you can actually see what's behind, how they actually write those function, those code. And the third level of open source, I think ultimately what we really want is the data to be available to the public. So what kind of training data they use? Can we duplicate, retrain our model from scratch? And so none of that for DeepSeek right now. We only have the model. We don't have the code or the training data. Hopefully, I think what we hope is if they're really open source, we would like to see the actual code. So so that's the excitement about the DeepSeek-R1 is we want to see how we are able to achieve this, right? So let me actually go back to the model architecture to see how we are actually what is the model made of. Um, let me actually go back to um, DeepSeek V1. So because V2 V1 continue to build on top of each other. Start with DeepSeek V1. What's unique about this model is it introduced a unique activation function called the sweet glue. So first of all, for those of you who already know the transformer or large language model, we know that all the large language model is a transformer or decoder only transformer. So with the decoder only transformer, you have a stack of layers, the so-called transformer block. In the block, there are two major layers, attention layer and the feed-forward layer. And so in the classical transformer, you have a so-called JALU function to transform the neurons. The activation function is mostly people use JALU or ReLU. So the first change they made in Llama 2 and also adopted by DeepSeek is called the sweet glue. So sweet glue is introduced a so-called swish function multiplied by a linear function of the weights. So WV are the weights. You essentially swish function is the input x times the sigmoid function and times sigmoid function applied to the input variable x, and the w is a linear parameters. So this is the activation function they adopt. And the second change in the on top of classical transformer is large language model is they also use so-called rotary position embedding. Remember, we in the classical large language model, we do position embedding by convert every position integer into a vector. And typically there's a formula, cosine sine transformation. We do so there's a direct mapping from the integer to a vector. So that's just we know every position is different. So we added the position embedding on top of we added that to the token embedding, the actual token, the word come in plus its position. So that gives us a recording of where this particular token sits in the long sequence in the sentence. So instead of position, the normal position embedding uses sine cosine, they introduce this called rotary embedding, where they use this complex number based on whether the position is even or odd. So you can also think about it. It's rotating the position by certain angles, and there's a formula defines that position. We talk about this in the Llama 2 meetup when we talk about this, the intuition behind this. But so these are the two things adopted by DeepSeek version 1, R1. One moment. I just want to see the time. Okay, we are halfway. The third thing is in the transformer model, we use so-called multi-head attention. So so if you think about the blue tokens, each is a token. So you think, suppose you have 8 words in the sentence, each represented as a token here. From here, they are mapped to so-called key value, QKV, query key values, right? So actually, sorry, this is the query. So there's an input I didn't show here. So the input will be mapped to 3 vectors, which is a linear transformation of the input query called the query key value. And because we chop them into different chunks, and each chunk you can call it a head. A head is just do a parallel computing when you calculate the attention from the input to the output. So classically, the traditional transformer is called a multi-head. Now people then realize maybe we can simplify the computing instead of like doing all these separate heads. So there is a so-called multi-query attention, where you only separately calculate the queries, but the key and the value are aggregated together. And then there is a compromise in between, is you group key and value in a smaller, with a smaller number of then has a small numbers than the actual queries. So this is just reduce the computing. So this is called the group query attention. Essentially, it's just a different way to parallelize the computing and make it faster. This is and this is adopted by the DeepSeek. So essentially, want to just emphasize 3 major change from classical transformer, and all actually started by Llama 2. And so DeepSeek following the same kind of convention. These three updates on the previous model. So that is DeepSeek V1. Now, after V1, we said that they see that the 70 billion model is not, actually the V1 is a 67 billion, a little smaller than the Llama 2. So their performance is okay, but not as good. They want to actually create a bigger model, a much bigger model. A bigger model has the advantages. The larger you are, the higher performance you can have. The only problem is the computing, right? When you have a lot of neurons, you have to certainly use more computing resource and run much slower. So this is where people come up with the idea of a so-called mixture of expert. So what it means, I want to show you this architecture. So the mixture of expert is first of all, the The transformer is it's still the same transformer with duplicated blocks. And there's one more change here is instead of using classical layer normalization to transform the value, so attention and the feed forward are the two major layers, but in between you do the some layer normalization. So instead of doing layer normalization, which normally is minus the mean divided by the standard deviation, they use root mean square normalization, where they don't actually minus the mean, so you ignore the mean, directly divide by the sum of all the values in that layer, and take a square root. So that is a root mean square for so it's much faster. It still do some normalization, but it's much faster. So the major in version 2, the major advancement, because it's 230 billion models, we cannot use all the neurons in the feed-forward network. So we divide them into groups. Each group is called expert. So when we say top K, meaning each time for any instance, for any input, we actually send them to a few experts. We don't use all the neurons to process. This set K can be 2, can be 4. Many models use top 2. So I think in this paper they use I believe it's top 8, because they have a lot of yeah, they have a lot. They use top 8 because they have a very large, very wide lot of neurons here. So they actually have 256 groups, 256 experts for the larger model, for the later model. For the version 2, they have a smaller number of experts. So what they do is so this is the first invention, and the reason they added this DeepSeek MOE is they said their mixture of expert is different from classical mixture of expert. So in the classical mixture of expert, you simply divide into expert, and then you route into expert. But they have these actual tokens on the beginning. These tokens is commonly like shared by all the experts. And so they basically said this is different from what other people are doing, called the shared expert. Personally, I don't think this make too much difference. It's interesting, but it's not really, personally, I don't think it's essential. So they do have this shared expert here. So that's a mixture of expert part. In the attention layer, they introduced so-called multi-head latent attention. We talk about the input goes through so-called attention layer, do the ROPE, the rotation position embedding. But before that, just pay attention to the bottom. Before you actually do the attention calculation, you have a so-called latent layer. The latent layer essentially just a linear transformation of the input. They map to a smaller size of vectors. So this is just reduce the computing. I think that's the main purpose of to reduce. After that, they divided that into different attention head, like the classical way to do that. So how much this contributed to additional performance? I personally don't think it make much difference. I think it's a fancy way to do the multi-head attention. We can just easily do this simple group query attention without too many like transformation. Maybe it's good for their computing, but in terms of performance, I actually have a picture I didn't copy here, where they showed that their performance is so this much bigger model, 236 billion model, is actually not doesn't perform as well as Llama 3 70 billion model. So which basically says either of this mechanism may not be that essential. So what I observe with development of large language model is that the architecture, there's not much fancy or additional research needs to be done inside the large language models. Architecture can be as simple as possible. For example, Llama 3.1, the 405 billion model has no mixture of expert. They're just a dense model. So they didn't even do the routing. They just do simple connection, dense connection, connecting every neuron to the input neuron. Very simple. So a dense connection certainly always better than this we call sparse connection, where you only connect a subset of neurons. The dense connection, a dense connection requires more computing, but it's much more consistent. The result is consistent, and the result is more optimal. So so personally, I think for the open source model, do we actually need a mixture of expert or not is still a question. At least for this, their expansion here that doesn't actually help that much, because they were comparing to the 70 billion model, a dense model. So that is my simple comment on this version 2 architecture. Now, version 3, they dramatically expanded the model. So the model size, I think it's maybe inspired by Llama 3.1 because in Llama 3.1, we started to see 400 billion models. So they said, why not we do a much larger model? If Llama 3.1 can do 400 billion, we can do 600 billion. Of course, there's a computing cost. There's a lot of things we need to worry about. But the deeper the model, the larger the model, always the performance will be better, ideally. So DeepSeek V3 is this gigantic model with 61 layers, and they are trained on close to 15 trillion tokens, which is the same as Llama 3. So Llama 3 and 3.1 trained on 15 trillion token. The DeepSeek V3 was trained on 14.8 trillion, so close to 15 trillion, almost identical. In terms of and then they went back. There's another thing interesting part is instead of using, one thing I didn't mention about the fine tuning. So when we fine tune V2, they use the supervised fine tuning. So you have a set of labeled data labeled by human. Let me see. So in the V2, yeah, they use the supervised fine tuning and then DPO, direct policy optimization. So DPO didn't use a classical reinforcement learning. So that's for V2. However, in the V3, they went back to the classical reinforcement learning, RLHF. Let me actually explain what. So the RLHF, typically after we pre-train the model, we train the model on like 15 trillion tokens. That's unsupervised learning, where the goal is to predict the next token for all the sentence, all the articles that we see, and that's totally unsupervised. So after that, we want to do so-called the fine-tuning. The fine-tuning is we create some small data set for so-called supervised fine-tuning, where you have a label. If the label typically are question and answer. So if you give the model a input, a user question, what should be the best output. So we have a set of data that tells us what would be the good output. So that's called the supervised fine tuning. When we feed those data into this pre-trained model, where the model performance will improve. After that, we are going to do a reinforcement learning to continue to fine tune. So in this stage, the reinforcement learning is we first have a so-called reward model, where you let the model itself generate two possible answers, and the human just vote good or bad. This in this way is much faster than create the supervised data set. So in the reward model, essentially it's accept or reject. So it's very easy to create a lot of training data based on the human approval or not. And so that's called a reward model. And when we have those good or bad data, we can, so in this stage, we can create a lot of data because the data itself was created by the language model itself. So we can let it generate a lot of like yes, basically every time generate two answers, right? So that's and then human, it's very easy for human to give a sum up and sum down. So this is called a reward model training stage. After that, we do a reinforcement learning. So once we finish this, so this is a separate model. We actually have another small neural network to tell us whether the two input is good or bad. So this is just a binary classification model. From there, you have a language model where you use the reward model as a signal to basically train the original the beginning this language model. And there are many ways to train this. PPO is just one method, one way to use the reward to update the model parameters. So that is a classical reinforcement learning with human feedback. What's interesting is they gave up. They did I think maybe they realized that this classical reinforcement learning RLHF still perform better than the previous direct policy optimization, where people think we can get rid of reinforcement learning, just jump from here to here, right? So they and instead of using reinforcement learning, they directly trying to model whether this is good or bad. And so that is the DPO, which I don't have time to get into. In one innovation for this version 3, DeepSeek version 3 is they invented a slightly different version of reinforcement learning method. So if you see here, the classical reinforcement learning method is called the PPO, also invented by OpenAI. It's called the proximal policy optimization. So it's trying to use use the reward signal to update the parameter, use a proximal range. And so actually I show you here. So this GRPO is called a group. Just they use the so-called group signal. So instead of comparing, so they started with a so-called old model called the pi theta old. That's an old model. And then they sample capital G is a number of samples. It's a group. So in the group, they have, say, group G equal to 10. You sample 10 response. Using this, they get the average, the mean of all the minimum values. The basically is a ratio between new model and old model. And this new model, the ratio between new model and the old model multiplied by so-called advantage parameter. And this advantage parameter is estimated from the average reward. Essentially, it's how well it does against so far, right? all the examples so this is going from 1 to 10, and so you add up all the examples, and then this so-called clip is just give you an upper bound that you cannot go beyond 1 plus epsilon, or and cannot go below 1 minus epsilon. So you basically get a clipped number. If you go beyond, you just take this 1 plus epsilon. So it's bounded your basically says you don't update your model too much. If you update too much, the model will become unstable. So it's using an upper bound and a lower bound to force into a certain region. And this KO divergence is basically the you also have this. This is more like a regularizer to make sure you also don't go too far away. So use this to regularize the total magnitude of your update. And so that is also the difference between your new model, pi theta is the new model, and the reference model. So that's basically the basic idea. In this V3, they said they invented this GRPO. Essentially, it's a simplified version of PPO. They use this the group average to update. So that is the major invention for. Personally, this is my personal opinion. I don't think also this makes big difference. The GRPO, whether it's PPO, people, you can do a little bit improvement. I think it's mainly computing wise, it's faster because you can quickly calculate, and without doing and this moves faster when you have a group of data to get the average, so it converge much faster. So this is a computing advantage. All right. So then, even with the V3, they showed that they are approaching O4O, but still not as good as the newer model O1. O1 is I mentioned is come out in September. V3 is December, so it's after O1 already released. So they said, how can we keep improving the performance, right? So in general, last week, this R1 is released. Now, one thing I want to mention that even though people are very excited about DeepSeek-R1, personally, I think because R1 is actually a larger model than O1. The OpenAI O1 is actually not big. It's a medium-sized model based on, I think, people's estimate, or even the OpenAI never publicly say how large their model. We believe the O1 model is between 300 billion and 600 billion. So it's a smaller model than V3, than DeepSeek-R1. And so if DeepSeek-R1 perform better than O1, it's reasonable. It's totally still fall into the law, the scaling law, where when you have more parameter, you always do better. That's just the fact. Also, in terms of let me see. Okay, I will just talk about the training process. I didn't write it down here. I will just talk about the training process. So the major training process here is remember in the paper, in the R1 paper, there is a so-called R1-0, where they first try to do the supervised fine-tuning. Let me go back to this picture. They get rid of step 1. They jump into step 2 and 3 directly. Actually, just step 3. Yeah, they use a little they use a rule-based reward, so they don't even need to learn this classification, the reward model. Reward model is a binary classification model, so they don't even need to learn. They just have a rule that for mathematics, for coding, it's very easy to know whether it's correct or not. So they have a manual rules to give you correct or not answer. So they directly apply reinforcement learning, and they want to see if they actually can do better. It turned out the R1-0 doesn't perform well. And they said they mix different language together. It's very hard to read. The readability is not there. So I want to spend the time on that, the R1-0. The real work is the R1 itself. So because they see now supervised fine tuning are still very important, they went back to this standard steps. So in the R1, what they did is they first created a few thousand, which they call very small supervised data set to begin with, to basically put when you have even a small amount of fine-tuning data, it's very good. It's very easy because most large language model after pre-training, they already have a so-called zero-shot learning capability. So they're very smart already. When you just do a little bit supervised learning, they perform much better. So after that, what they did is they have two kind of reward function. One is I mentioned the rule-based. Then they have so-called another for translation, for question answering. They created a reward model. So they are trying to learn that human to judge yes or no. So they created 600,000 training pairs actually for them to learn. So they use this reward model, then do the so-called group GRPO, the group the policy optimization. With that, and after that, they use their the V3 model to generate a sample data to generate so-called supervised data. So they repeat. Essentially, they do these 3 steps twice. After they train, they went back to use their own model, the V3 model, to generate close to 800,000 training pairs, the supervised training pairs. And I think that significantly improved their performance for mathematics, for coding, particularly those competitive data set. And that is their major success. So they did another round of supervised learning, then they did another round of reinforcement learning, and then they got their result. So that is the whole training process for DeepSeek-R1. One more thing I want to mention is for V3, the supervised training data is 1.5 million. For R1, they do 2-stage. They did the 2-stage, 2-stage supervised learning. In the second stage, they use 800,000 supervised training pairs. So that give them the performance we see today. And let me continue. So that give them the performance that we see here. However, I want to say what will be the next. What we are saying is I think we are O1 performance is good, but it's still not ideal, because if you see here for software test, a software bench, which is just a software programming test, it's about 40%, 49%. It's not as good. And also in this PhD, even though it's superhuman, it's only like 71, 75%. However, if you look at O3, which was released around the Christmas time by OpenAI, it's a like dramatic improvement against the O1. So O1 is here, 83 for the mathematic competition. O3 is 97%. For the PhD, O1 is 78. O3 is 87, close to 88%. For software engineering, I mentioned before, it's 48. Now it's 71. So essentially, they did an excellent job in software engineering test. In the code competition, DeepSeek-R1 reached the 2029 ELO score. The 3000 is the perfect score. O1 reached the 1800. The O3 is almost perfect. So essentially, I think certainly it's a superhuman performance, almost perfect, right? If you look at, we mentioned in the beginning of 2024, coding math are still struggling, but now the coding is close to perfect. Software engineering, essentially they can do their own coding, they can do their own debugging, all these tasks what a software engineer can do. So that is what we need to watch out. DeepSeek right now, DeepSeek-R1 is at the level of O1. So it's even though it's very sensational, there's not news. It's not as good as O3. O3 is ahead, way ahead of O1. And the real interesting question is, are we going to see open source catch up with O3? If by that time, I personally, I think it will take a few more months, maybe half a year, for open source to really reach the O3 level. By that time, I think we can say, oh, the open source model will be competitive with the closed source model. So that's my take on this. Okay.